So, hello everyone. My name is Jakob Martin, and today I'm going to present our EC3 paper titled Aligning Heterogeneous Views, Stakeholder Terminology and Multi-Level Mappings in the AEC Industry. And the central topic of this paper is how different stakeholders described, structure, and use information about the same physical asset and why this creates problems in the wall building process. So I will start off with the core problem. So for example, here in the center, we will find one physical asset. So for example, a door. And however, the same door can be represented very differently depending on the stakeholder. So for example, on the left side, we will find a stakeholder A, could be an architect. And in the planning process, the architect is attaching different kinds of attributes to this kind of door. So for example, attributes like overall width, fire resistance rating, and global ID. And on the bottom, for example, we find a stakeholder, for example, a structural engineer who has different kinds of requirements, or a fire safety engineer that wants to check the model for pass and fail outcomes. And on the right side, we have a stakeholder C, for example, from the facility management, which has different kinds of requirements for the same physical door. So for example, asset IDs or different kinds of maintenance intervals or spare parts that need to be like serviced. And these kinds of different representations, they actually introduce a lot of mismatches. So for example, we have the terminology mismatch, where we have different kinds of synonyms or abbreviations. We have different kinds of encoding mismatches, where different kinds of units, standards, and formats are used. And we also have a structural mismatch, where one attribute at one perspective becomes another entity. And the result of that is that mapping these different perspectives together becomes difficult. We have duplicated data, wrong checks, and a lot of manual rework. So to put this a little bit more into perspective, we will find, for example, the design model on the left side, where an architect sits down and creates an IFC door type 1. And in compliance checking, there are different requirements added to this. So here we find, for example, the AE30 fire rating. And as soon as this door has been opened, because this is an escape route, we will find that there will be a fire alarm release, and we need a clear opening width. So these are the requirements, for example, for compliance checking. And in the facility management, we have different kinds of parts regarding the door for the maintenance schedule, spare parts, and the warranty record. And the problem here, again, is that we have the same door in three representations, and none of these representations really talks automatically one to each other. So obviously, there is an implication for an AI-supported system to solve this kind of issue. So the first step here would be identifying the fitting perspectives. So where the data actually lives and where it is needed and what actually is the exact integration goal. And here, for example, like mapping the design perspective to the facility management maintenance. And for that, we created a typology decision layer and to classify these different kind of mapping types. So I named them here, but this is the focus of the work, and we will talk about this in detail in a couple of minutes. And the next step, obviously, would be the candidate generation. So we have that type-specific evidence where, for example, persistent IDs, spatial context, operational metadata, and value patterns apply. And on the last step, when we have a validated mapping, we can use it for downstream use. So we have human-in-the-loop validation in ambiguous cases and provenance and different kinds of metadata for the auditability. So the mapping typology we've created has 5 core mapping types. And obviously, this can be expanded even further. So this work has is not complete, and of course this can be expanded in the future. So the first type would be the direct entity correspondence. Then we have an attribute to entity transformation, cluster-based mapping, granularity shift, and value in unit normalization. And the first step is the most obvious one. So here we speak about the same physical reference with 2 different entities. So for example, here on the left side, we find the design perspective, where we have the IFC door with different kinds of attributes added to it. And on the right side, we have the operations in facility management, where this becomes a door asset record. So the important point is that both entities refer to the same physical door, and they come from different systems, but they serve different kinds of purposes. So this allows us to explicitly link these two representations together. So for the next type, we have the attribute to entity information. And this is where the simple alignment basically stops and where we cannot simply rename the attributes. So on the left side, for example, in the architect's perspective, we have a fire rating, AE30. And on the right side, for the checking compliance, this becomes a requirement. And there we need different kinds of layers of information. So for example, different kinds of standards, scopes, rule logics, and there it becomes its own entity with context. And this is actually a more sophisticated type, and this is where it becomes really complicated. So as a third type, we have, for example, the cluster-based mapping. So in one perspective, in the design perspective, we see different kinds of doors. And for example, door 1 to 8 with different kinds of GUID attached to it. And they're all on the first floor. And on the right side, on the construction side, we will actually find that mostly these are referred to an installation package, for example, P17. So we see that we also have, with these different kinds of mapping, different types of aggregation and segregation. So for the next type, this looks somewhat similar at first, but this is the granularity shift. So for example, in the architect's model, the may is represented as IFC door with a number of attributes, but in the facility management perspective, the same door is not only relevant as one object, it is broken down into different kinds of objects. So here we find, for example, the door leaf, the frame, the different kinds of hinges, lockset, and closer to it, and different kinds of needs attached to these simple, like broken down structures. So we also need to preserve the relationship here, and this is also what makes it kind of complicated. And for the last type, we will find the value in unit normalization. So here we have the same concept, but different encoding. So for example, in the design perspective, we have an area with defined 240 square centimeters. And on the right side, on the facility management perspective, a different kind of area with a different kind of value attached to it. So here we have, for example, 0.024 square meters. So this work in general is derived from respective scenarios. We have different kind of scenarios taken into account: planning, construction, operations, and the coverage is obviously bounded. So we don't have any claim for completeness. And out of scope for this kind of work obviously was the geometric conversion, different kind of coordinate transformation, and different kind of schema translations. And the mapping needs in general are bounded on a project-specific context and organizational project conventions. And the future steps for that towards the implicated AI system is that we want to do this on a larger scale and test this on a data set and actually verify these different kinds of mapping steps. And there is also another work coming up, which is called a pre-mapping decision model for reference linking in the AECO workflows. So there we did the first testings on a very small data set to actually verify and use this derived mapping topology. Thank you very much for your attention. Are there any questions?